elaborate on that, but you basically had a transmitter and receiver, and you just moved it over, and you got 0 crossings here in the response when the when the transmitter or the receiver was directly over the loop. You also got another 0 crossing when the transmitter was over the loop, and so you were able to actually kind of sketch out this curve. This curve is basically geometry, so you can sketch all of that out just by drawing, your currents that are induced and kind of seeing, oh, it's positive here, it's negative here, it's positive. Okay? But then there's actually 2 curves, 2 responses that you could get, which would then be an end phase and a quadrature phase. So here's different responses that you see. And then once I've got this particular curve, then there's actually, when I'm measuring the data, I could measure both an in phase and a quadrature phase. So if my induction number is 1, then that in phase and quadrature phase they're identical. However, if the induction number is small, or smaller, then you can see that by this response, the dashed line here, which is the quadrature, is actually larger than the real part. So what does that translate into? That translates into the fact that when I'm taking my instrument and I'm moving across like this, and Samantha is the pipe or whatever like that, I get this kind of a curve, but I get 2 of them with the quadrature actually being larger compared to the real. So it's a low induction number. On the other hand, if I have a high induction number, then it's the real part that's larger. So that you can see here, that response, the real is larger than the imaginary, and hence the curves. Okay? So I think that is a pretty good summary, and I think because people have already done the labs, now you're kind of like, okay, I sort of got that. And you have this 3-loop path. So far, we've only been talking about one thing, and that is that, okay, I've got a transmitter, so again, I'll use Samantha. I'm trying to find her, and we can see that I've got all these coupling kinds of things and get currents that are induced in her. But the question is, what actually happens if Samantha is buried in something that is also conductive? In other words, what is the background? What is the effect of the background conductivity on this? So we need to look at that. So if we think about what we're doing, here's our transmitter coil, here's a receiver, and we've got the Earth. The Earth is just like a conductor. But we have kind of thought about, looking inside the Earth and saying, oh, well, I've got a little bit of a target here, or maybe I've got a pipe, or something like this. And here's the transmitter, here's the receiver, and here's my. But actually, the Earth could be, just some kind of conductivity in which which is buried. And from the physics of what we're doing, conductor is a conductor. So it happens to be spread out uniformly, doesn't matter. So Faraday's law is still going to hold. If I have a time-varying current in here, time-varying field, that's going to induce current inside the Earth. Those currents are going to generate magnetic fields that I can measure there. So nothing changes. It's just the geometry. But now, what we're going to do is to try to see, well, what's the depth of investigation that I can see? So suppose I've got, a sphere or something that's buried in here, and now if I have conductor on top, then from what you had seen when Soggy was talking, was that, oh, the electromagnetic fields decay as they're going through there. So it may be, I may get to a point where I can't even see this guy. So we're going to be greatly affected by this background conductivity. So we need to kind of understand what the effects are. So here's basically the slide. There's a lot of things that are in common here with what Soggy had said. So this is the Earth-air interface, this line here. And if I've got a electromagnetic wave out here, let's suppose it's at 10,000 hertz or something, then it actually has a wavelength that's equal to the speed of light divided by the frequency. So it's got a particular, so c, the speed of light, we did that in GP. So that's what happens if you've got a wave outside. The moment that it goes inside, however, it now starts to propagate in. And if you have a high enough frequency, you have that GPR thing, and it just sort of propagates as a wave. But if we have lower frequencies, then this wave actually diffuses in. And so it goes in a certain skin depth. It kind of propagates in only like a wavelength or so, and the wavelength is really short. So if the conductivity here is 0.01 Siemens per meter, 100 meter, the velocity is greatly decreased, and the wavelength has really decreased. So these dimensions aren't to scale, but you get a wave outside, and then it kind of diffuses inside. And then the thing that we had that was really important was this quantity called the skin depth. So that was the depth to which the field has decayed by 1 upon E of its value. So we had this particular formula here. The skin depth is about 500 square root of the resistivity over the frequency. So the skin depth is really an important part because just as in the GPR, you can only see into the Earth like 1 or 2 skin depths. So there is an app. I'm not going to show it to you. In fact, there's 2 apps. There's one in which we have a transient wave coming in, and there's another that we have a sinusoidal harmonic wave coming in. And you can use that to explore what the waves are going to be like as they go in. From our particular case, what I'm interested in exploring with you is, okay, what happens if we just have a loop source? That's what we've been talking about. And the loop source is going to give us a magnetic dipole, right? So remember we had, so if we have a loop like this, so we've got a current coming around like this, then it gives rise to something that looks just like a magnetic dipole. So here's the magnetic fields. So it's exactly the same. Just a magnet. Okay? We're going to be concerned about the orientation of this with respect to the Earth's surface. If this plane, if this loop is parallel to the Earth's surface, I suppose this is the loop, so it's like this, then the magnet or the magnetic field, it's like a vertical magnetic dipole, right? So I got a loop current, it gets replaced by a magnet, looks like that, so the magnetic fields go up. So a horizontal loop gives rise to a vertical magnetic dipole. And sometimes we'll shorten that by VMD. So you'll see this, vertical magnetic dipole, and that's going to be what happens if you have horizontal. Remember, we also talked about coupling, right? So if I'm going to, again, explore, what's happening at this front row, so maybe I'm trying to see Alan here, I've got a horizontal loop, right? It's got a vertical magnetic field, so I'm going to excite you in some particular. If I turn this guy, so it's like this, now I've actually got a horizontal magnetic dipole. So that's going to illuminate things really differently. But that is also something that is very useful. So we're going to also call that horizontal magnetic dipole. That's not it. So let's first of all explore this guy here, the vertical magnetic dipole, because that's usually what's done. The instrument that you're going to see and use actually the one that's used so much in like the geotechnical industry, where you're really trying to look only in the top few meters, is an instrument called the EM31. And that just simply consists of, so it's an EM31, it's got a boom. You saw the picture of it in the lab. So there's a transmitter here, and there's a receiver here. This thing is about 4 meters like that. The transmitter is transmitting out something about 10,000 hertz, and generally you just kind of strap this thing on and you just kind of walk like that. So you're looking at a horizontal thing. So let's just take a look at that and see what happens. So we're going to look now at a target, and what I want to do is to show you what the effects of the background conductivity. So let's suppose we bury this target. So let's suppose we bury a sphere, and we've got a transmitter that's sitting above you. Just do that. So we don't know what the motivation is. So here's the idea. I've got this, and I've got a transmitter that's sitting like this. So this has got a current in it that's going like that. If I change this current, okay, then there's going to be time-varying magnetic fields, and there's going to be currents in the earth, and those currents are going to also be circular in kind of in that same plane. So my induced currents are going to also be kind of circles that are sort of going into and out of the board. And if I have an object down here like this, so some kind of a conductor, I've got these time-varying fields coming in here. I'd expect to see some currents, on this object. So I'm going to be really interested in, what are those secondary currents on the object? I'm trying to illuminate that. If there's no conductivity between here and here, so it's air, then what I see is something like this. So it illuminates the outside of the sphere. I've got currents that are here. Now, there's actually quite a few things that are going on. First of all, you notice, the currents are just kind of at the top part, and part of that reason is that we've got just a little loop up here, and the magnetic field from the loop falls off as 1 over r². So by the time we get down to something that's deeper, our primary field is smaller. Okay? So that's one of the things we see. So we illuminate the top portion more so than the bottom. The other is that we get currents that just seem to be on the outside of the object. And we had a little bit more time in this course. We can talk about this a bit more. But the bottom line here is this has got some conductivity sigma or resistivity rho. And if you're going to have something that propagates in on here, what's that relationship that we have that tells you how far into a conductor an electromagnetic wave can propagate? Anybody? Liam? Ricky? So remember when Saudi was talking about I need to propagate an electromagnetic wave in, what was the thing that you always wanted to evaluate to see if I can see something? So this always holds. So it actually even holds on this sphere. So if I'm trying to get electromagnetic energy into the sphere, if my conductivity is really large or resistivity is low, then I find I can't really get stuff in very far. Okay? So now we're starting to understand this picture a little bit more. So here's my induced currents, and those currents are going to give rise to magnetic fields, and I might be. Now watch what happens when I change the conductivity of this background. So now I'm going to start to make this thing more conductive. So I still have my sphere, but I'm going to make this more conductive. So what do you think is going to happen? Anybody? Michelle? Oh, what's going to happen? I'm going to try to put a wave, electromagnetic wave in here, but I'm going to put some conductive material on top. Yeah. I'm sorry? Yes, and why? Partially that is correct, not quite what I'm looking for.
Currently more inclined to go to the ground. It's more inclined to
That is also pretty close. This is just a conductor. Remember, we have this skin depth thing here, right? So if I'm trying to put electromagnetic energy in here, it's also governed by the skin depth. And if this thing is conductive, then that primary field is going to be decaying by the time before it actually gets the sphere. And so at some point I might not even see it. So those are the things that we're going to kind of look for. I'm going to put material on here so this is now free space, it's 10 to the minus 8 siemens per meter. If I make it a bit more conductive, make it 10 to the minus 2, don't change things very much, because the skin depth is still pretty large in here. So let's increase it again. And now look what happened. So here's a 10 to the minus 1 siemens per meter. So now the background is getting conductive. You can see how it's starting to shield things. I've got currents that are being induced in the background host material. And look at my sphere, it's not shining up as bright. So that's an important visual takeaway here. If I'm going to look at something that's at some depth, I'm going to need to worry about what the overburden conductivity is, or what the background. And if I go even more, so now I make it really conductive, now I don't see anything. So we kind of come back to what we were talking about before. This, we're trying to see this guy here, but the skin depth in this background stuff is so small that I'm not even reaching that. So I'm trying to see, Samantha, if this is just too conductive, the waves just going to, they just disappear before they even get to it. So we don't even have a chance to excite you and generate currents there. Okay, so that's the takeaway. Yep.
If you have an insulator that's supposed to on the surface, won't that also not get the current or object?
No, actually. If I make this really resistive, there's no effect. This is the big difference. This is so important. I'm going to spend a moment talking about this. So let's suppose I've got this kind of guy here. Okay, I've got, let's say, some kind of a target, and I've got a really resistive layer in here. When I did the DC resistivity, I put in a current, right? Here's another current, here's my A electrode, here's the B electrode. And if I had a resistor in here, it didn't go through, right? That was our problem, it's a shielding problem. Kind of like that, right? So I couldn't see this coming. In this particular case, and I'll show you an example in a second, this is just resistive. So there's no currents that are induced, there's no loss of electromagnetic energy. So I would expect in this case, I'll show you an example, that we actually might see this. So there's two, it's both electrical, we're looking for electrical conductivity, but if we do it with a DC technique, we're able to observe certain things. If we do it with an electromagnetic technique, we can see others. So that's the kind of big takeaway message here. We're trying to find something, but how we can find it or whether we can find it or not, it's going to depend on the background. So that's a simple. So just to kind of recap what we've kind of learned here, we've got looked at the basics of EM inductions, we've looked at response functions, mutual coupling, we talked about the data for frequency and time domain systems, and we've talked about the circuit. So there's quite a few questions. If we had a little bit more time and we might come back, these are some things that would be kind of fun just to go around and consolidate things. But think about these questions, and we'll come back to them before we actually do the final exam. But you know, here's the essence. I think if you can answer these questions, you're probably good to go. Like for instance, you know, what does Ampere's law really say? What's the magnetic field of a loop of current? What is meant by the term magnetic moment as far as the relationship between the current and the loop? What does Faraday's law say? What is magnetic flux? Why is Lenz's law important? What's that minus? What's meant by mutual coupling? What is the response function? And how does it influence field observation? There's actually quite a few things, but we kind of looked at each of them at some point. So take a look at these questions, and then we can come back later on when we start to review. The good thing about this course, I think, and we've tried really hard to do that, is it's front-end loaded with the material. Because once we finish EM, then we've got one lecture on IP, and then we're done. Like, we don't have any more new material. So that gives us a good 2 weeks just to kind of relax and go back and, you know, kind of look at things and make sure that we understand some of those basics. So here's some questions that can help you. Okay, so now that's the basics. So let's look now a bit at the survey and the data. Electromagnetics really has a tremendous kind of scope and capabilities for the kinds of problems that it can handle and also the different kinds of systems that are out there. DC resistivity was just really simple. I put a current around. Electromagnetics is a lot more versatile, and that's why it's going to be so much more useful in the future. So we've got a source, and that source is going to put in, you know, a waveform. It could be a harmonic waveform like this, or it could be some kind of transient waveform. So this one's got it. In here, the current is on, and then it's switched off, and then there's no current in the loop, and then it's on, usually in the reverse direction. So these are different waveforms, but the physics is the same. Like whenever I've got a time-varying current, it's going to induce currents. And then, with respect to the source, you can also put it all kinds of places. You could have it in the air, it could be on the ground, and it could be an inductive source, like we've sort of been talking about with the loops, or it could even be, you know, a grounded source. So there's a whole bunch of different ways that you can configure it. We're going to be talking most about the inductive source, and I want to ground you in this EM31. And then the transmitters, if they're airborne, so here's a frequency domain system that's being towed across large areas or rugged terrain, and here's a time domain system that's also being towed. Sometimes you actually put big loops on the ground. In Manitoba, there's a place called Lalor. Done a lot of geophysical work, and they have a loop. They just go up, put a loop on the ground, and this is a big loop. This is like a couple of kilometers on the side. So it's got a pretty massive magnetic moment. And yes, you put a current in through that, and then you can measure the magnetic field. So there's 4 bodies underneath here, and you're trying to see if you can't find those guys. And you can measure the data on the ground or up in the air. So that's the transmitter: frequency, time, in the air, on the ground. The main thing with these transmitters is the moment. That was the product of the current times the area. The other thing that helps with airborne things is that you can wrap a wire a number of times around in a loop, and that effectively increases your. The receiver, I'm not sure whether we talked about this before, but it could be a magnetometer. We certainly did this at the beginning. And it could be measuring like any of the 3 components of the magnetic field. So that's just the same as we've done at the beginning, of course. You can also measure with a coil, as we did in the lab. So you're basically measuring the voltages, or you're measuring effectively the change in magnetic field through that. In time domain experiments, we end up having something that looks like this. So here's a current, it's on, then you switch it off, and then you just wait. So the moment that I switch it off, okay, so we saw this in that small 2-coil lab. The moment that I switch it off, I've got a current that's in my target, and it just decays away. So our response function kind of looks like this. It starts off at some point and then just decays away with some particular time constant. And again, from the point of view of the receiver, it could be mounted on this system up here. So this is a SkyTemp system, and here's the receiver. Or it could be flown in through the air in a separate survey. So here's that big loop that I talked about just a moment ago. And now we put in a current that looks like this in through the loop, and that's going to induce currents inside the Earth. And then you can just measure this with a total field magnetometer carried by this, let's say this helicopter that's going back and forth. So that's kind of an interesting experiment. You've got a source on the ground and you're actually measuring. The other is, so that was with time, you can also do frequency. So in the frequency domain, you now have something exactly what you had in the lab. Your transmitter is just this sinusoidal frequency. And you really don't want to have that in your final signal. What you really want is just the signal that's coming from this from this target. So somehow we're generally trying to get rid of that primary signal and just measure the secondary field that's coming. In most of the frequency domain systems that we work with, they kind of emulate what you did in the lab. Like they've got a transmitter and a receiver. It's probably a little hard for you to see, but each of these is kind of color-coded. So there's a transmitter coil here, so this is at 40 kilohertz, and there's a receiver coil over here. So each coil is separated by a different distance, and each coil has got its own frequency. And in this case, there's 5 sets of coils at anywhere from 140 kilohertz down to 400 hertz. So it's quite a range. We look at the frequency spectrum. So this is 400 hertz to 140,000 hertz. So that spans quite a different range. And the reason that you do that kind of comes back down to this skin depth thing, right? So we've got 500 root rho upon f. So the low frequencies here have got a bigger skin depth, so they're going to see deeper. The high frequencies are going to see shallow. So that's the big ticket, right? So just as Sagi was talking about you have a particular frequency, it only sees in a small depth. If we lower that frequency, we gradually see farther. So that's generally how these systems are. We need to get rid of that primary field. So we either subtract it out by knowing what's going on, or we sometimes have a little bucking coil that removes that primary. At the end of the day, we're going to end up with just the ratio of a secondary field to the primary. Yep.
For that, the resistivity need to be constant.
I'm sure.
Are we assuming that resistivity stays constant in that case?
No. So what I meant by this, and this is important enough to spend a moment. So let's suppose I've got an Earth here with, let's see, row 1 and row 2, okay? And I've got a system up here, and I want to see, maybe I want to see something in here, or maybe I just even want to detect whether, what this resistivity is down here, and find a particular thickness. So here's perhaps the simplest thing, and you're going to have to do this in the lab. Let's suppose I got the following Earth structure. I've got row 1, I got row 2, and I've got a layer thickness H. Good. I want to find all 3 of those values. So let's suppose I was able to control the frequency. If I get a frequency here so that delta 1 is equal to well, I can even get rid of these guys here. So here's my skin depth formula. If I choose a frequency that's high enough, then really the only thing maybe that I'm going to see is, if I look at my electromagnetic wave, it's just going to kind of go down to 0 here. So I'm going to get a response that's really affected only by this upper. So high frequencies, so maybe that 140 kilohertz is just going to see, the top couple of meters. And if that top couple of meters happens to be 100 meters, that's fine. If I lower the frequency, now my EM waves, are going to penetrate more deeply. And now I'm going to start to see something of what's going on down here. And therefore, my signal that I'm going to be here is going to be sensitive, not only to this resistivity and layer thickness, but also to the resistivity underneath. So that's the basic concept. And it's very similar to what we had in DC resistivity. Remember, if we had the electrodes that were really close together, then, I'm just seeing a little bit here, right? Can't see them. If I make them a little farther apart, I kind of see that. But way far apart, I get all the way back to, say, where Liam is. Okay? So that's kind of like a sounding principle. The same is true here, except that all we're going to do now is change the frequency. So if I'm going to start off at a really high frequency, my waves just decay. They're attenuated. I don't even get down now. If I make lower frequencies, I see through. And if I get all the way, very low frequencies, I can see right to the back of. Right? So these are kind of like important concepts. You get these guys, and then most of the other stuff falls. So we're going to actually work a little bit with the simplest of all of these experiments. It's something called the TM31, and it's going to look like this. Show you just mount it, sling it on over your shoulder, and you got a transmitter at one end and a receiver at another, and you're just going to walk it through and measure the data as you go. just to give you some idea about what these things look like. So here's an airborne EM survey. So this is called a bird, and kind of get a sense of scale by the number of people who are there. And you can have different kinds of coil systems. So these are horizontal coplanar systems, vertical coplanar system, and as I said before, you've got a number of these coil pairs that work so that you end up having, for each coil pair, works at a particular frequency, you get like a real and imaginary part, datum, for that frequency, and then you have different frequencies, so you get the chance to see. The term that you're going to see a lot, and if you're talking to any contractor who's providing you data like this, they're going to talk about this thing. It's called a sounding curve. So we had this in DC resistivity, which we just talked about by making things. In EM, depending upon which system you have, whether it's a time domain system or it's kind of on and off, each sounding curve is going to be effectively the measurement of data that's in this off time here. So when primary field is off, then you're just going to measure a signal. So what's happening here is in this current loop, we have a current, and then you switch it off. The moment I switch it off, I get all these induced currents. And then I'm going to measure the magnetic field, some component, at a receiver at different time channels. So generally you pick, as far as times, maybe 10 microseconds after shutoff, just to put things into perspective. So the time scales here. So after shutoff, okay, and this is time. So this, your first time channel might be 10 microseconds, and your last time channel might be, I don't know, 10 milliseconds. So maybe 3 orders of magnitude in times, but you want to sample as early as you possibly can. And where the industry is right now, and they're trying to push this more and more, is to kind of get that earliest time channel. The earliest time channel correspond to high frequencies. High frequencies correspond to very shallow skin racks. So that the earlier that you can measure, the more resolution you have near the surface. And then the sounding curve is just, here's your signal as a function of time, in this case, 10 to the minus 2. And it's just some curve. Those are your data. Just those are your values. Okay? So this actually contains the information about the electrical resistivity. We're going to need to do that. In the frequency domain system, then we've got, as I've just talked about here, a number of different frequencies. And if I was able to do that at a whole bunch of frequencies, I'd have something that looks like this. So the black part is the real things, and the red is the imaginary or functions. So again, in frequency domain, you always have 2 numbers. You got a real and imaginary, right? And in the time domain, but that's your sounding curve. So your contractor will tell you, like, okay, here's a particular sounding curve for this system that's sitting out here, and it's going to be something like that. It's going to be data, and usually those are log data. So notice how much they're changing. This is 10 to the minus 7, and that's like 10 to the minus 13. So it's like 5 or 6 orders of magnitude. And then times are also going up. So that's your sounding curve. This is the guy that contains the information about your conductivity. So you need to dig that out. At this point, that's the sound. In the frequency domain, your sounding curve actually is like 2 curves, because there's an in phase and a bunch of phase. But again, this curve contains the information about the conductivity, and that's what you're trying to what we're seeing now, especially over the last 4 or 5 years, is systems that look like this that are now being flown over large areas of the country. In California, for instance, because of the water crisis that's there, there's movements to fly this system over the major part of the Central Valley in California, which actually is important to Canadians, right? Because most of our food, most of our produce comes from the Central Valley of California, and we get produce really inexpensively because we grow it there. However, what they're doing is they're pulling out water at this huge rate such that the water table is just continuing to drop. At some point, you can keep making your wells deeper, but at some point, you just can't do that anymore. And at that point, then you run out of water. You run out of water, you ain't going to have no agriculture. So this is a really important problem worldwide, but there's places that are happening that's really important for us right now. And the thing that's really crucial about this is the top couple hundred meters. Because, and you'll be happy to know that Dr. Kang is going to go to Stanford to work on this following problem in conjunction with people there. They always have these, like, we're either drought or we got deluge of water. And if you had looked back this last year at what happened in California, which is kind of in a drought, but there are times when there's just massive amounts of water that are coming down. And that stuff is coming down so voluminously, it just runs off. And they can't store it. So not only does it run off, it's carrying with it all of the sediments and all kinds of stuff that is important, and it just sort of exacerbates it. Okay, so that's a bad situation. And just to give you some idea about what's happening, they actually refer to these things as atmospheric rivers. You can look that up on Google, an atmospheric river. And what you'll see is this intense accumulation of vapor, okay, that's sitting up at X kilometers above the Earth. It's maybe 100 kilometers wide, and it's 100 meters thick or more. And that thing has got as much water flowing through it as the Amazon River. And that comes on land, hits the mountains, dumps. So you can imagine the Amazon River, okay, dumping on you. What do you do? Okay, so it's a tough problem, but you gotta know what you're up against. So the thing that Swami's going to be working on, he should probably tell you this, is the following, that, well, in fact, geological engineers, you'd be interested in this, right? So you got tons of water that's coming down, and maybe you want to capture it somehow, okay? So I want to capture this and have it percolate down into the ground. So you need to know what is the thing that you need to know. So suppose I have a reservoir here of water, I captured it, and I want to let it filter down. What do you need to know? Filtration rate and the property that's kind of connected with that? The hydraulic permeability, yes. Okay, so that's what you need to know, and that's going to depend upon what kinds of materials you got in here. So are these clays? Are they sort of aquatards? Are these sands? Or what are they? Right? So you don't really know. So what you need to do is to characterize at least the top 100, maybe a couple hundred meters, so that you know that, okay, if I store water here, that in some reasonable length of time, this stuff is going to go down, percolate down. So that means I need to differentiate between a geology that has got, you know, some clay aquitard here, and, you know, something that's just got sort of sand and gravel, right? Because it ain't gonna flow down here, but it could be here. So now the task is, okay, so let's fly the whole interior part of California with this airborne time domain EM. Let's try to figure out which parts of this, you know, might have a hydraulic conductivity that is such that stuff could percolate down, and which is going to have aquitards, and then to try to build it up. So all of that stuff is connected in these curves. Okay, so you fly over, you measure these curves here, 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 and then now you want to take that, you're going to process that, you're going to convert it, and you're going to try to decide from a geologic perspective where you might want to store the water. Okay, so we'll pick that up from there next time.